All right, welcome to the first session. Everyone get ready to learn about in-memory event resequencing, realistic testing for impossible bugs. And your speaker, Glyph.
Hi, everybody. Bad news, everyone. Distributed systems are super hard. And we're going to be exploring a lot of really fast talking and really small fonts during this session. So I hope nobody's trying to get some work done on their laptops. All systems are distributed systems now. There might have been a time when some of the systems that you were programming were not distributed systems, but unless you're still programming one of these things, that time is probably gone. So if we're all programming distributed systems, what exactly is a distributed system? It is Satan's computer. A network under the control of an adversary here is being used in the technical sense, meaning user, is possibly the most obstructive computer which one could build. It may give answers which are subtly and maliciously wrong at the most inconvenient possible moment. For example, when one is plugging into a projector at a conference. So how do I know if I'm building a distributed system? Let's say you don't believe me, you think that you're just a software developer, you're not a distributed systems engineer. It's easy, you could just grep your code for this one simple line. If your code imports requests anywhere, then you're building a distributed system. Or anything else that performs the same function, of course, the twisted equivalent being no exception, but we'll get to that in a minute. Okay, so of course, all programs that use requests anywhere is a bit too abstract a collection of programs to talk about, so let's choose something specific. Meet Bob. Some of you might remember Bob, the author and star of the sleeper hit MMO World of Bobcraft. Bob's players, such as Alice here, are fantastically dedicated to the game and would like to be able to purchase more in-game wealth using real money. Bob has his own motivations for wanting this feature. Conceptually, the workflow is very simple, deceptively simple even. We have a function, buy game bucks, we bill the customer, we give the customer their bucks. Great. Talk over, everybody have a great conference. So the first problem with this implementation strategy is that it's too slow. Payments can take literally days to clear, and users are likely to abandon a transaction if it doesn't complete within seconds. So customers need their game bucks right now, billing takes forever, and we need to get off the main thread, so as the word thread implies, threads to the rescue. The first thing that we can try in this situation is to farm out the work to a couple of different threads so that the calling thread does not need to block. At the risk of wearing out a cliche, if you have a problem and you think now I'll use threads, you are at the risk of wearing a few cliche, think threads, have problem, to problem, think, problem, problems. So jokes aside, there is a serious problem with this implementation, which is that confirm payment blocks until the customer has confirmed the payment. The consequence of this bug is that Alice gets infinite money. She just calls the GameBucks API a million times, never confirming the payment, and then waits for the game server to crash so all those GameBucks will never be taken away. Of course, this rather ruins the point of real money trading to begin with, so let's fix it. So how are we going to fix this bug? Well, the first thing we need is a state machine. So this state transition is very important. We begin in good standing, then we request game bucks. Now we owe money. While the player owes money, we don't want to let them buy more game bucks. We want to be optimistic about the first transaction. But when their payment clears, they go back to being in good standing again, and they can buy more. So okay, let's try to implement this fix. So this is a fixed version, kind of. It still has a pretty important flaw. Since this is a bit much to walk through on one slide, like I said, a lot of code, really small fonts, let's just zoom in on the give gamebucks function. If we look at just this part of the example, we can see a pretty big problem. If the function starts off by asking the customer if they're in good standing, then we proceed right on through. Now, Alice has a slightly tighter race condition to win now, but all she needs to do is to give GameBucks to run as many times as possible before getting to that owes money now method call, and she'll owe money a whole bunch of times, but she will get as many GameBucks as she can make requests. And if you think players can't make requests faster than you think they can, you might never have worked in the entertainment industry. So as with all threaded code, if we don't see locks just everywhere, we know it's probably not right yet. So let's just put locks everywhere. So this is an attempt that scatters some locks all over the place in the hopes that it will help us coordinate the relevant critical sections. You'll notice that as we converge on a correct multi-threaded solution to this supposedly very simple problem, the font size gets smaller and smaller and smaller. But the question we have to ask ourselves now is this code correct? Let's zoom in on one of these lock acquisitions and see if it's doing the right thing. OK, so we grab the customer lock. If the customer's not in good standing, we need to wait. If the customer is in good standing, we don't need to wait, but they owe money now. That seems good. We have a critical section that's covering the check of the flag and the setting of the flag. So great, it's fixed. Bob runs the code in production, and as far as he can tell, Alice is no longer scamming free game bucks out of the system. But if we want to be sure, of course, we've got to test it. The obvious strategy to test this fix is to use a fake lock with a fake customer. So in the fake customer, you can check if the fake lock is being held. Such a mock customer might look like this. All good. We got a flag. We just check to make sure that it's held in the relevant places. Except, of course, as time goes on, holding the lock might cause performance issues, and someone might helpfully come along and change the code to do this instead. The lock's still held in the places where we check, the test will still pass, but the logic is totally wrong now. So the fundamental problem here is that running code sequentially in order is never going to be quite the same as running it in parallel. There's a way to fix this one specific mocking strategy. You could give the lock a counter, make sure that it's the same counter in both places, check that the lock's held in both places. But that still doesn't really tell us anything about the correctness of the logic that we're testing. It's just testing the implementation detail of the lock we happen to be using. So running the same code in sequence with different mocks that respond in different pre-programmed ways is not the same as actually causing the interleaved execution of the application code. In short, you cannot write a failing unit test for a race condition between threads. You can write a test which dies with an error, which locks up your test suite, which crashes your test machine, but those are not quite the same thing. I mean, that still tells you something. It's still useful, but it's not the same thing. So the next potential solution is end-to-end testing. And I want to be clear, because it sometimes gets misinterpreted when I talk about this type of testing strategy. I would not say end-to-end testing is bad. End-to-end testing is great. It's necessary, even. You need to do it. But the reason you need to do end-to-end testing is you need to use it to discover bugs. Once you found them, end-to-end tests are never a good way to reliably reproduce them. In an end-to-end test, there's always too much going on. So the second testing strategy for doing this is to abuse end-to-end testing and make tests that are too real. Of course, too much realism isn't really a problem. You always want your tests to be as realistic as they can be. But the problems are, if you've got tests that are too real, they run too slowly, and they fail unreliably. So we're stuck between the rock of too much mocking and the hard place of too much realism. What do we do? Where's the Goldilocks middle ground for testing everything accurately, quickly, and usefully? So in order to get an answer to this question, we need to back up and ask ourselves, exactly what about the system under test are we trying to verify? What are the scenarios that can happen? So the answer to that is there are a set of discrete external events that can occur to customers. One thing that can happen out there in the real world is the customer can ask us for game currency. They can say, give me some fake money. Another thing that can happen is we can receive confirmation that a charge went through. In other words, that a player gave us real, actual dollars. And the third thing that can happen is that we can receive confirmation that a payment has failed. Now, we're not going to cover the failure case, but just to kind of enumerate the things that can happen, for our first pass here, we're going to just transform these three enumerated events into three simple skeleton methods on a class. OK, so class, it's got three methods. It's valid Python. But of course, you can hide a lot behind an ellipsis. So at this point, you might be wondering, what about requesting money from the player? That does need to be represented, but that's something that we request from another service, not an input to our service. So we can sort of hand wave over that in terms of what we need to test here. Now that we've got a language to talk about the events which might occur to a customer, what is the question that we want our test to ask? It's a little bit nuanced, but it's simply, What happens when a customer requests GameBucks, then requests GameBucks again before payment for the first request is cleared? So this is just an ordering question. What happens if these two things happen in sequence without this other thing happening in the middle that we would assume would happen in the middle pretty fast in normal execution? So at a high level, that question in Python might look like something like this. We have a service, we have a customer, the service gets a customer request to get some GameBucks, and then we assert something about it. But again, you can hide a lot behind one of those ellipses, so we're not quite high level enough to tackle this problem yet, so let's level up. This example is super abstract, so let's get down to brass tacks. How does the customer know about the GameBucks service object to tell it when money was received? How does the HTTP client work? I hope the last slide has convinced you this might be a good idea, but there's obviously a lot of details about how all this is wired together, which you might need to get specific on before it's a useful strategy. So let's talk about the passage of time. Much simpler example. You set a timer for 5 seconds, and you kick off some work in the background. You think it can't possibly take 5 seconds until one day it does take 5 seconds, and then it actually takes like an hour. So that assumption is correct until one day it isn't. Twisted.internet.task.clock is a class within Twisted that simulates the passage of time. It allows you to use the same interfaces as the real implementation, but with a controllable temporal flow. So in order to show you how this is done in a real system, I'll take you on a whirlwind tour through Twisted's testing facilities. This is going to go fast, but mostly I want you to know kind of what the words mean. You don't need to catch the nuances of everything. So first and most importantly, clock is what we call a verified fake. There are tests that apply to the real passage of time in Twisted that also apply to clock. It's an implementation of the same interface, which does no I/O. And verified fakes are a really nice thing for library authors to provide. Kind of independent of the notion of event-driven testing, you might want to consider adding some of these if you maintain a library. I can tell you that Twisted doesn't have nearly enough of them yet, and every time we add one, users rejoice. So clock and reactor both have this call later method, which causes a given function, f, to be run later. One brief slide is definitely not enough to cover deferreds. But the idea is that they're an object which might have a result in the future but don't have one now. Defer later is a little utility that kind of bridges the gap between these two APIs, deferreds and call later. It's an event-driven version of time.sleep, so it just means do something later and then give me an object that will have a result when that finishes. In the normal implementation of the call later method, of course, time just passes. But with clock, time is frozen. It is totally under your control. So it has this one extra method that the real implementation does not, which is to advance a given number of seconds. So before we talk about how testing should work, the first test case in Twisted's testing history made the same mistake that I'm talking about making here, which is that we made everything super realistic. So the actual test case class in Twisted is unfortunately the one you shouldn't use. The slightly wordier synchronous test case is the one that provides facilities for interacting with deferreds in a deterministic kind of controlled way. So it has a couple of APIs. The first is assert no result, which simply asserts that a given deferred has no result yet. That might not seem very interesting, but in the case of, for example, rate limiting, it's kind of interesting to know that your response has not yet been received, because that's what you're testing. Then there's this other method, success result of, which pulls out the result from a deferred. Now, the reason this is a method on the test case rather than the deferred itself is in a proper event-driven program, you react to the event being received. You just say, hey, when you're done, call me back. In a test case, you actually want to say, no, this is done now. This is the exact moment that I expect that this deferred should have a result. So for my example here, I'm going to demonstrate how a simple rate limiter might be tested. Just to start off as clear as possible, we're rate limiting a thing here. So a thing looks like that. It's got a do method. The do method returns a deferred that fires when the thing is done. And we have this rate-limited thing wrapper here, which has a do method, and to test if we want to ensure that do is not called on the real thing too quickly. So the underlying thing is self.thing. And there we go, all the pieces I was talking about. We've got our reactor, which is our clock that controls the passage of time. It reacts to the passage of time. We use defer later to create our deferred. When the deferred is fired off, we increase our delay because there's more work outstanding, and then later when the work is done, we decrease the delay again. Now, this is not a very good rate limiting algorithm, but it fits on a slide, so I'm going with it. We can test this thing using twisted internet task.clock, which here is being wrapped by defer later. And here you can see we just construct our fake thing. Our fake thing has a list of outstanding requests, which in the test we then make sure that it's being asked only when time has passed, the initial delay being 1 second. So we advance the clock by 1.1 seconds. Our outstanding request list goes from 0 to 1. We make sure that it has no result. Then we give it a result from the test. The test here is acting as the event loop. It's controlling everything that happens. And then finally, we make sure that the success result is the result that we just gave, and it is available at that moment in time at the end. So I should note that unlike the earlier kind of hand-wavy hypothetical examples about threads, that was 100% real. Those tests passed. I know because there are people sitting in the front row who would totally call me out on it if they didn't. This type of testing seems very kind of advanced. It's like people will often throw around terms like vector clocks or causality when talking about systems like this, but it does fit on a slide. It is simple enough that you can use it as a normal human. So time passing is all well and good, but the interesting part of a distributed system is when data is sent to or received from some other node on the network. The verified fake in Twisted called memory reactor implements methods like connect TCP and listen TCP, which enables you to participate in kind of a fake network. However, memory reactor and its peer I/O pump are low-level facilities that are mainly of interest to infrastructure developers, people implementing the low-level protocols. So I'm not going to cover them directly here, because that would be really tedious. And instead, I'm going to talk about what they enable. Trek, which is Twisted Requests, is a request-alike API that includes a module, trek.testing, that uses the real implementation of Twisted's HTTP client and server on top of the fake implementation of TCP networking. This allows for a very high level of realism with exactly the level of determinism and performance you would expect from a pure unit test. Maybe a little bit slower, but close enough. So here, we've got an example of a server and a client that we might want to test together. Again, this server is kind of more of a test mock. It's just got a list of pending outstanding operations, and the client talks to it. Notice the client takes a trek as a parameter. It does not import trek and then use it, because in our test, we're going to create the server. We're going to wrap a stub trek around it, and then we're going to use the client with that object. Stub trek behaves exactly as though you were making requests to something, but it wraps a server-side object that you just provided in Python. So here, we make the server, we make the client, we make the request. We assert that the client request does not have a result yet, because it shouldn't, because nothing has happened yet. We then call the flush method on the stub, which turns the crank on the fake network I/O, which allows all the requests to be sent and the response to be received. Then we check to see if there's a success result, and hopefully there is. Again, this is a 100% real test. This is a real thing that runs. But of course, just testing a test mock with the existing client library is not interesting. Ultimately, you want the Ouroboros of a client that calls another server, which itself has a client that calls another server. So let's ensure that the behavior of the middle server is correct. That's where interesting application logic lives. So here, we have a front end. The front end is a little client application. Klein, in case, sorry I glossed over that on the previous slide there. Klein is a sort of twisted Flask-alike, uses the same routing syntax. So we have a route at the root which makes a request to /A and /B on our backend, awaits the content of both of them, and then returns that as the response. Our backend is really simple. It's just got a list of deferreds for A and a list of deferreds for B. This is our test mock in this case. And now we have, this is the setup. We make a backend. We connect the backend to a stub trek. We make a front end. connect the front end to a stub track, and then we flush it so everything's all set up, and then we have a check which makes sure that the request that was made has the content hello world. If you can't get all of this, if you get the gist, it's fine. The important slide is the next one, which is we can then test that this API works, whether it's A that fires first as a response, or it's B that fires first. Both of these are now tests that you can run. And now that we've leveled up enough with these fake example problems, we can reorder our events back and forward. It's time to confront our original problem. And this is as short as I could make it, so please bear with me. So here we have a proposed final customer object which implements all of our methods. In good standing is just defined as a property indicating they don't owe us any money. Got game bucks just implements our bucks counter, and payment cleared ensures anyone waiting on the good standing deferred gets called back when our balance has been restored. So first, let's check out what happens with a broken implementation. So this is the same bug, more or less, that we encountered at the beginning. We call good standing, but we don't wait for it to complete. So infinite money for Alice. Call this request, she can call this as many times as she wants. It'll check whether she's in good standing or not and do nothing with that result. It'll just proceed straight into getting game bucks. Her balance will go up and up and up, but not in time for us to actually charge her. So next, let's look at a test. In this test, we issue 2 API requests to give the customer 1,000 game bucks each. And what happens when we run this against the buggy implementation is it fails, as expected. The customer's bucks counter is 1,000 greater than it should be. So now we can fix the implementation. And the way that we fix this particular bug is we just have to await the customer being in good standing, because if they're in good standing right away, it's optimistic. They start off in good standing. We're just going to proceed right on through. And now that same test will pass, because we have constructed a scenario where the test is asserting about the interesting events that are happening in the infrastructure, the real things that are happening on the network that cause the game bucks to be requested, that we can then control the order of their execution and make sure that we end up in the correct state at the end. And Bob lives happily ever after. So I was not sure how long this talk was going to be, but looks like we got through it in time, so I think I will be happy to take questions now. And given that I blew through some of those code slides pretty quickly, if you've got a question about one of them, I would be happy to go back and take another look at one.
All right, as Glyph said, we have some time for questions, so please come up to the microphones if you have a question. And as a reminder, please make sure that your question is actually a question. I'm sure Glyph would be happy to talk about the talk and hear your thoughts, but let's do that out of the track.
Yes, a question is something to which you do not know the answer.
Hello. Any chance of using this deterministic testing outside of Twisted Universe?
So the specific technologies covered here are kind of Twisted's proof of concept of the deterministic testing concept. However, the general idea is definitely usable within async IO. It's definitely usable within Tornado. Anywhere that you have an event loop whose execution you could potentially control, you can definitely kind of draw a line around your eventual result object and then turn the crank. One of my hopes for this talk is that it will stimulate a discussion about doing this throughout the Python ecosystem rather than just kind of as a twisted thing. I'm hoping we're blazing a trail and not off in our own corner.
Thanks.
If you know which particular sequences you're worried about, sequences of events, then I can see how this would work. But in a realistic application, there's probably a huge, when you're looking for race conditions, there's probably a huge variety of possible combinations of sequences. How are you going to read? It's combinatorial explosion of them. How are you going to actually write those tests to make sure you cover the race conditions?
So that's actually a great question. And the idea with testing using this strategy is that this is a way to write your unit tests and your regression tests. It is not a way to do your integration testing. It's not a way to discover the bugs. However, There are two strategies for discovering the bugs. One is you do load testing in production, and you just run lots and lots of code in parallel and see what happens, get tracebacks, and then kind of back it into tests like these. That's the hard way. The easy way is to use something like Hypothesis, and to use so Hypothesis is a generative testing framework in Python, which you can use to generate orderings. If you have a sequence of events that you want to run in a variety of orders, you have Hypothesis generate the orderings and do discovery on the state space of your application. The really nice thing about doing that, I haven't managed to do it myself, but I've seen a couple projects start to experiment with that approach. When you do that, you start to get some of the benefits of like Haskell-style quick check, but in a development environment that's kind of as fast and loose and dynamic as Python. It could be a really powerful combination.
Interesting. Thank you.
Thank you.
Hey, Glyph. Two questions. The first one's just a clarification. When you call clock.advanced, does that run the reactor somehow until everything is settled into the new time value?
What it does is, effectively the clock internally is just a sorted list of functions to call at particular times. So it just jumps forward in that list to the point where its time value is now greater than the last one that was going to be run and calls all the functions in turn. So they all, many of the features of this deterministic testing strategy will have all of the code that's interesting runs under a particular stack frame. So when you call clock.advance, all of your application logic is running just under there, and if it blows up, and the normal reactor would catch any exception coming out of a call later. Clock will just let it propagate and like blow up, and you get a traceback that comes out of your test.
Cool. The other question is, I'm curious about mocking at above the TCP layer between TCP and HTTP. I wrote a mock framework for MongoDB that resembles this a lot, but it actually opens up listening ports on localhost and connects to itself over TCP rather than mocking at a layer above that. So I'm curious what your thoughts are about the relative strengths of mocking out the socket layer.
So that strategy where we would open local ports and talk to them directly was the original way that most of Twisted's test suite worked. And as far as I can tell, it is in every way worse. If you want to do that type of testing, what you really want is an integration test that actually has separate processes kind of like coordinated with something like Siege, or like it's actually a load test. If you do like individual small tests with sockets, it's thousands of times slower than doing it in memory, and you can't control the execution fully because the operating system is doing stuff behind your back with those sockets. You run out of file descriptors. It's just kind of it's a big mess, which you can manage, but once you've got a complete enough mock of your network I/O, there's really no reason to.
Thank you.
Okay, so when have you gone through an end-to-end testing and just set it up to say, all of these things that may take some time to complete, let's pick totally random times? Or is this really what the Hypothesis tool is doing for you?
So I think Hypothesis is what you'd be looking for if you wanted to do something like that, because that you would, if you want to have variable times and not just like, well, this thing might run first or that thing might run first, then having a framework to generate all of the variable times and discover the interesting boundaries, which is really what Hypothesis does, is it runs a bunch of different cases and it reduces down to the cases that actually are meaningfully different. So that's probably something you would want to investigate.
Okay,
Yeah.
thank you.
All right, everybody thank our speaker.
Thank you all for coming. Great questions. Appreciate it. It's a bit too abstract a collection of programs to talk about, so let's choose something specific. Meet Bob. Some of you might remember Bob, the author and star of the sleeper hit MMO World of Bobcraft. Bob's players, such as Alice here, are fantastically dedicated to the game and would like to be able to purchase more in-game wealth using real money. Bob has his own motivations for wanting this feature. Conceptually, the workflow is very simple, deceptively simple even. We have a function, buy game bucks, we bill the customer, we give the customer their bucks. Great. Talk over, everybody have a great conference. He's trying to get some work done on their laptops. All systems are distributed systems now. There might have been a time when some of the systems that you were programming were not distributed systems, but unless you're still programming one of these things, that time is probably gone. So if we're all programming distributed systems, what exactly is a distributed system? It is Satan's computer. A network under the control of an adversary here is being used in the technical sense, meaning user, is possibly the most obstructive computer which one could build.
All right, welcome to the first session. Everyone get ready to learn about in-memory event resequencing, realistic testing for impossible bugs. And your speaker, Glyph.
Hi, everybody. Bad news, everyone. Distributed systems are super hard. And we're going to be exploring a lot of really fast talking and really small fonts during this session. So I hope you're nobody. So the first problem with this implementation strategy is that it's too slow. Payments can take literally days to clear, and users are likely to abandon a transaction if it doesn't complete within seconds. So customers need their game bucks right now. Billing takes forever, and we need to get off the main thread. So as the word thread implies, threads to the rescue. The first thing that we can try in this situation is to farm out the work to a couple of different threads so that the calling thread does not need to block. At the risk of wearing out a cliche, if you have a problem and you think now I'll use threads, you are at the risk of wearing a few cliche, think threads, have problem, to problem, think. It may give answers which are subtly and maliciously wrong at the most inconvenient possible moment. For example, when one is plugging into a projector at a conference. So how do I know if I'm building a distributed system? Let's say you don't believe me, you think that you're just a software developer, you're not a distributed systems engineer. It's easy, you could just grep your code for this one simple line. If your code imports requests anywhere, then you're building a distributed system. Or anything else that performs the same function, of course, the twisted equivalent being no exception, but we'll get to that in a minute. Okay, so of course, all programs that use requests anywhere is